Welcome to Structural Dynamics class. In this class, we will study approximate methods for finding first natural frequency of multi-degree of freedom structure. So, till now we have studied multi-degree of freedom structure, how to find out eigenvalues and eigenvectors. So, that is natural frequencies and mode shapes of the building we have found out. Now, usually first mode carries or first natural frequency carries lot of information, like maximum mass participation will be usually in the first mode. So, if we know the first mode without going to the tedious procedure of calculating matrices, so we can find out the maximum forces and maximum displacements which are occurring on the building or due to the action of external forces. So, we will discuss two techniques in this class, two techniques of finding approximate natural frequency of the multi-degree of freedom system. So, we will discuss Rayleigh's method and we will discuss Dunkerley's method, and we will solve one example problem in each method and find out how approximate these methods are compared to the natural frequency of the structure. First, let us discuss about Rayleigh's method. So, in Rayleigh's method, so this is dependent on the energy. So, if we look at the total energy, we already know that total energy is the combination of kinetic energy of the system, a vibrating system, plus potential energy of the system. So, potential energy and kinetic energy together is total energy. So, if we write the equation for that, it will look like this. So, as you can see in this equation, E is equal to half m u dot square and half k u square, where m is the mass of the structure or mass of the system and u dot is velocity and u is the displacement. So, half m u dot square half k u square, this is the total energy of the system. Now, if say kinetic energy is maximum, so that is first component, Ke is maximum, so potential energy will be 0. Why? Because when displacement is maximum, velocity is 0, and when velocity is 0, displacement is maximum. It is something like this. So, here that this is a displacement response u versus time. So, at this location displacement is a maximum value and velocity here is 0. So, tangent of this curve is velocity. So, velocity is horizontal here, so that is 0, 0 slope. Here velocity is high, very high, high value, where displacement is 0. So, that means what? For maximum kinetic energy, that is Ke max, potential energy will be 0, and similarly for maximum potential energy, kinetic energy will be 0. So, at this location potential energy will be 0, this location is of maximum displacement, so kinetic energy will be 0, and this location is of 0 displacement, potential energy will be 0. So, kinetic energy will be 0, potential energy will be 0. So, kinetic energy is maximum, potential energy is maximum at these locations. Now, from this one, using this principle, we can write that, so half k u max square, that is half k displacement maximum square, that is maximum potential energy, that will be equal to maximum kinetic energy. So, that means what? Total energy is equal to kinetic plus potential, but maximum kinetic energy is equal to total energy, maximum potential energy is equal to total energy, that means two maximum values must be same. Then here we are making an assumption of displacement function. So, since we are discussing about multi-degree of freedom systems, so displacement is not of a point mass, but a series of point masses like that. So, we define u is equal to phi and q. So, phi is a spatial quantity which is described at a discrete locations of where center of mass is there, and then q is the time variation. So, q of t and phi of x, so that is u, so displacement u. So, we can write u as phi sin omega t as a displacement function. So, u dot, that is velocity, response is phi omega cos omega t. So, if we substitute these things and look at the maximum values, so displacement maximum value will be phi into this sin omega t maximum value is maximum minimum value will be in the range of -1 to +1. So, if you take minus or +1, the maximum value will be u max will be equal to phi itself. And then if you take say u dot max, again this cos value maximum value is again 1. So u dot max is equal to phi omega. So we have maximum displacement value and maximum velocity value. So if we take these two things and substitute back in the equation 1, so what we get is half m u max, so that is phi omega square, that is equal to half k phi square. So since this phi is a vector, what we get is, so this k into phi square will become phi transpose k phi, and here omega comes out, phi transpose m phi it will become. So with this we can write omega square, that is omega square is coming from, say, half gets cancelled, m by k we can put here. So this I am rewriting this equation here, half omega square phi transpose m phi, left hand side, right hand side is equal to half phi transpose k phi. So half gets cancelled. Now from this one we can get, so omega square is equal to phi transpose k phi by phi transpose m phi. So this is called Rayleigh's coefficient or natural frequency, first fundamental natural frequency using Rayleigh's method. Now why we are calling first fundamental natural frequency? Because we use here mode shape 1, first mode shape. Okay. So then we can call it as first fundamental natural frequency. Instead of phi we use, say, second mode shape, so then we get second fundamental natural frequency. So let us discuss what are the properties involved in that. So if phi is the exact mode shape, then omega will be exact frequency. If phi is the exact mode shape, then omega will be exact frequency. So here in this case phi, say let us take 3 degrees of freedom system. So 1, 2, 3, we can assume any function. So we can assume straight line function, we can assume parabolic function, we can assume, say, sine function, any function we can assume to get the first fundamental natural frequency. This should be approximately near to the first mode. So if we make it approximately near to first mode, then we get first natural frequency. So if phi is the exact mode shape, then omega is exact frequency. So in this we are not evaluating mode shape, we are assuming some mode shape, and then with that we are getting like approximate fundamental natural frequency. So any mode shape whatever we assume, that cannot give the exact, so the lower value of energy. So that means what, any mode shape we are assuming, that will be upper bound value of frequency. So that means what, whatever is the original frequency, we will get slightly higher frequency in the Rayleigh's method. So the salient features of this are, when phi is eigenvector, Rayleigh's coefficient gives value corresponding to that phi. So we can assume this as a first mode, or we can assume that as a second mode, something like this, or we can assume that as, say, third mode. So first mode, second mode, third mode, any mode shape we are assuming as phi, we will get corresponding natural frequency. And one important thing is, if the error in estimating phi or error in like assuming phi is of first order, then the error in Rayleigh's coefficient will be of the second order. So that means what? So there is an advantage, even though if error is slightly higher, but actual error in estimating the omega, that is frequency, is of the lower order. So Rayleigh's coefficient is stationary in the neighborhood of two eigenvalues. So it is bounded between omega 1 square and omega n square. So whatever mode shape we are assuming, so we will get in between that. So the next method, which is Dunkerley's method. So this Dunkerley's method is a lower bound method. So Rayleigh's method is the upper bound method. So let us discuss about second method, that is Dunkerley's method for finding approximate natural frequency. So in this, the fundamental frequency of multi-degree of freedom system is often of greatest interest than its higher natural frequency, because its forced response in many cases is the largest. So the Rayleigh's method, which gives upper bound to fundamental frequency, can now be complemented with Dunkerley's equation, which is lower bound method. So what is the concept of this Dunkerley's method? So it works with the flexibility coefficients. So one simple equation is there in Dunkerley's method, that is 1 by omega square is equal to m1 delta 1 plus M2 delta 2 M3 delta 3 plus so on like that. It depends on number of masses. So if we take say 3 degree of freedom system or 3-story building and we lump the masses at the center of mass locations or its slab locations and take stiffness 1, stiffness 2, stiffness 3 as column stiffnesses and then estimate this delta 1, delta 2, delta 3. So these delta 1, delta 2, delta 3 are flexibility coefficients. So now how do we estimate this delta 1, delta 2, delta 3 flexibility coefficients? As you can see in this one, so this is the structure, we need to find out delta 1, delta 2, delta 3. So delta 1 is like say this, there is K1 here, K2 here, K3 here, it is written here. So delta 1 is 1 by K1, delta 2 is 1 by K1 plus 1 by K2, delta 3 is 1 by K1 plus 1 by K2 plus 1 by K3. It is something like these springs are attached in series and wherever we are working, so below that masses are 0. So in this, while getting delta 3 flexibility coefficient, so M2 and M3 are assigned 0 and then we have 3 springs attached in series. So what we get is the from this one, this is the equivalent stiffness. So 1 by K1 plus 1 by K2 plus 1 by K3, K3 is the equivalent stiffness what we are getting. And for delta 2, M3 is 0, M1 is 0. So M2 is present. So when M2 is present, when M3 is 0, so anyway the upper one will be eliminated. So the equivalent stiffness of K1 and K2 will be 1 by K1 plus 1 by K2. So we get delta 2. This is the flexibility coefficient. And for finding delta 1, we have M2 0 and M3 0 and we have only M1. So since only M1 and K1 is there, so we get 1 by K1 as a flexibility coefficient. Now let us solve one problem and understand Rayleigh's coefficient, Rayleigh's method and Dunkerley's method. So in this one, determine the range of natural frequency of the given building for the particular mode shape using approximate methods. So building is given, so whose masses are M1, M2 and M3. So all three masses are say 2250 kg, which is the same example which we are carrying from the previous class. So K1, K2, K3 are 10.36 into 10 to the power of 6 Newton per millimeter. So now we are assuming this as a mode shape, as this is our assumption. So 1.8 and 0.445, this is our assumed mode shape. Now in Rayleigh's method, we know Rayleigh's coefficient, that is omega square, is equal to phi transpose K phi by phi transpose M phi. So upon substituting these values and mass matrix and stiffness matrix, if we substitute these values, so what we get is, so phi transpose M phi, we need to work it out. So phi transpose, this is a vector, so transpose of that, and this is a column vector, this is a row vector, this is a 3 by 3 matrix. So we got phi transpose K phi value as 3778064.08, that is the total value of that. And then similarly we evaluate phi transpose M phi value and then we get this 4142.77. So if we calculate omega square phi transpose K phi by phi transpose M phi, the value is 911.97. Then if you take square root, that is 30.2 radians per second. So this is natural frequency of first fundamental natural frequency using Rayleigh's method. You can observe that this value is almost near to the exact natural frequency from the previous class, you can observe, because we have assumed the same mode shape. So mode shape what is given in first fundamental natural frequency, we have used that. Because of that mode shape, we are getting like almost very near to the natural frequency. Then let us work the Dunkerley's method. So in Dunkerley's method, the equation is 1 by omega square is equal to M1 delta 1, M2 delta 2, M3 delta 3. So M1, M2, M3 are all are same 2250 kg and K1 is equal to K2 is equal to K3, that is equal to 10.36 into 10 to the power of 6 Newton per millimeter. So if we use that flexibility coefficients, what we get is 1 by K1 value 9.68 into 10 to the power of minus 8 and delta 2 value 1 by K1 plus 1 by K2. So then we get 1.98 into 10 to the power of minus 7 and 1 by K1 plus delta 3 as 1 by K1 plus 1 by K2 plus 1 by K3. So delta 3 value as 2 into 2.89 into 10 to the power of minus 7. So if we substitute all these values in the equation. So we get 1 by omega square as 1.3 into 10 to the power of minus 3 and omega as 22.7 radians per second. As you can see, this is a lower bound value. So this value is lesser than the exact natural frequency, and Raleigh's method natural frequency will be higher than the exact natural frequency. So one can easily find out the exact natural frequency will be in between this Raleigh's coefficient and lower bound method. So in this class, so what we have studied, let's summarize that. We have studied that how to find out the fundamental natural frequency, which is quite often used for finding the maximum forces and maximum deformations which might occur on the structure or structure might undergo. So for that we need first fundamental natural frequency. So we studied how to find out this fundamental natural frequency using two methods. So one is Raleigh's coefficient, which uses the energy in the mode shapes, and then Dunkerley's method, which uses the flexibility coefficients, and we have solved one example problem for understanding the same.